The second tool we need is we have to estimate the ANs in that power series. And to do that, we want to do it fairly generally, so we need to briefly talk about lim_sup and lim_inf. And there were a couple of people who haven't seen this in 131A, and also for others, I imagine that it doesn't hurt to have a little refresher. So the picture to have in mind is this Wikipedia picture that probably most of you saw, especially after the exam. So lim_sup, you can call it the best eventual upper bound. So in this picture, it would be this value that eventually bounds all these values. There might be some individual ones that are bigger, but eventually this is essentially a bound. And on the other side, you have lim_sup that plays the role of this sort of eventual lower bound of the range. So these are pictorially what these are, and what's crucial about lim_sup and lim_inf is that they're used when we don't know that the limit exists. Indeed, if the limit exists, these limits will coincide. So if the points will converge to a single value, then the best upper bound, best eventual upper bound, and best eventual lower bound will be basically the same, or in the limit will be the same. Therefore, these are actually the same concept. So if the limit exists, you use the limit. If it does not exist, or if you don't want to worry about it existing, you use lim_sup and lim_inf. And feel free to ask any questions, especially if you haven't seen. This is a bit of a quick introduction to this thing. Okay, so let's define these rigorously. So lim_sup is defined as this best upper bound, and how you do it is you take first the upper bound of all the indices, then you drop the first one, and then you take the maximum or the supremum of the remaining ones. And then you drop that term, take the supremum of the remaining ones, and you drop more and more terms until eventually in the limit, this is a decreasing sequence of things, you obtain what is the lim_sup. So you take upper bounds of indices after k, after an n. This is these lines here that were drawn, and then you send n off to infinity. So colloquially, yeah, what it is the best eventual upper bound. It's not an upper bound for all the indices because some elements can be above it, but it is an eventual upper bound in the sense that if you go a little bit above it, the indices will always fall below. So if you want to define lim_inf, it's defined similarly, and the picture would be sort of reflected is the limit as n goes to infinity of the infimum of after that index. And notice that these infima here define a sequence, and this is defined for sequences, this lim_inf. So in the exam, for example, you had I of Fn. This is your sequence, An. Okay, so it is useful when the limit does not exist. And the main lemma about that is the following. This is how you usually use this claim. So if you know that the limit superior is less than m, then there exists an index such that after that index, an is less than m. So contrary to limits, an doesn't have to be close to capital M or anything like that. It just means that it has to be less than that. So it's proven from the definition. Well, the picture is that, okay, we have our lim_sup. We have our capital M, which is strictly bigger. Well, you can put some line here in between these two things. This is you add an epsilon. And the sequence has to eventually fall below this line. That's the idea of the lim sup. And if it falls below that line, it also falls below, strictly below m. So there's a little bit of room there. So okay, let's fix an epsilon to be m minus lim sup an over 2. Therefore, there exists a capital N such that after n bigger than a capital N, the supremum k bigger than or equal to n minus the lim sup is less than or equal to epsilon. But this means that the supremum here, as kind of the maximum of all these numbers, has to be less than or equal to lim sup an plus the error. So triangle inequality, it's less than this plus the difference. But okay, so this is lim sup as n goes to infinity plus epsilon. But by our choice, putting the line a little bit in the middle, so the 1/2 there, we get that this is strictly less than n. So what this means is that the supremum is less than that. So now, if n is bigger than or equal to capital N, then an is less than or equal to sup of all the indices bigger than capital N, because an is contained there, which is strictly less than m. And this is exactly our claim. So we know much about lim sups, so this argument you should know. One thing about lim sups is that you have to worry sometimes about them being minus infinity. So I'll just mention that there is this case minus infinity. Without discussing how to prove it, because so in that case, the only an is going to minus infinity. That's the only possibility. I invite you to try and prove that. But then if an is going to minus infinity, this an less than m, capital M, is automatic. Any questions? Also, afterwards, sorry, I didn't get the chance to put it online before. Okay, just some quick examples on this. So -1 to the n is our canonical example of lim sup. It's the this sequence is bouncing above and 1. And the lim sup is the eventual upper bound, best eventual upper bound. Now the suprema would be all 0 -1, so lim inf of n to the infinity of -1 to the n would be -1. And there's a bit of a lag with this. So, and we stated that limit superior equals the limit if the limit exists. The limit superior always exists, just like the limit inferior. But if the limit exists, they are the same. This may not exist, and the -1 to the n is the canonical example. Okay, so what? Just to get back, so we had there was this main lemma, and in the interest of now saving a little time, I'll just recall the statement here. So limit sup n goes to infinity an is less than m is basically the same thing as saying that there exists in capital N such that after that index, an is strictly less than m. This is actually an equivalence. If you want to understand, you could try to do the other direction as a proof. It had two cases: when you're real, when you're not. You used a little bit of extra room. But unfortunately now we don't have time to go over it more despite the technical problem. I'll stick around at the end if you want to return to that point or anything at the first half of the lecture. But so, okay, we have -1 to the n, limit superior is 1, limit inferior is -1, and we stated that the limit is equal to an if the limit exists. Now you can come up with more complicated examples, such that lim sup n goes to infinity of 1 plus minus 1 to the n over 2n plus 1. And this, the way to think about this, another way, is that the limit superior is the largest limit that you can get from a subsequence. So it's the largest subsequential limit. So in this case, how do you make this expression largest? Well, you have to make the numerator large. And the only way to do that is by choosing the plus signs here. If you choose the minus signs, you get something going to minus a half. That would be the lim inf. If you choose all the plus signs, you get a half. I mean, this is not proof, but it's a heuristic of how to think about this. How do I get the largest values for this thing? And if you think of this, then there exists a capital N such that you can bound it from above anything strictly above a half. So this is eventually big less than 1/2 plus epsilon. But you cannot say it's close to a half. So it's kind of like an upper bound, but not. Now, some of these extreme cases is lim sup minus 1 to the n times n. So something that oscillates quite wildly, like that. In that case, the upper bounds, so the suprema, are always infinity. So lim sup is also infinity. You're not bounded from above. If you take just the minus side, then your values are going to minus infinity, and the upper bounds are going down all the way up to minus infinity. So you get minus infinity for this lim sup. So I know this is, if you have never seen this or thought about this, this is very quick, but hopefully this gives a sense. We don't need very much, and mostly this intuition will suffice. Indeed, so we want to state the root test because we'll be using that for the power series. So sum n equals 0 to infinity, an. Let this be a series, and this is a series of real numbers. It converges if lim sup of nth root of an is less than 1, strictly less than 1. As you remember, if it's equal to 1, the test is indeterminate. Now, in calculus, you will have seen this statement without this sup part. That's a weaker statement because it presumes that the limit exists. The fully general statement is with a lim sup because it always exists. It gives us a little bit more flexibility in applying this, and we don't have to worry about things existing. I mean, one example where this difference is apparent is if you have something that alternates between 0 and something. So your sequence could be, say, 0, at 1 it's 0, then it's 1/2, then it's 0 again, then it's 1/4, then 0, 1/8, then 0, ... Then this limit superior would be equal to 1/2 if this was my ANs, because it's measuring the upper bounds here, and doesn't see the lower bounds. So, okay. So how do we prove that something like this converges? I said it in this class also in 131A when I taught this was a big theme. We have to compare to something that we know converges, and with power series, it's always a geometric series that we compare to. So we want to find something that we can compare to, and the idea is that we want to compare an should be less than b to the n. So if you take the nth root, we want that really an would be less than b. So we want this. And this is what this condition is kind of meaning. So let's be careful. Okay, so let's call this actually the lim sup equals a equals lim sup an. It's strictly less than 1. So now if we fix any a strictly less than b strictly less than 1. I mean, for example, b is the average of 1 and a, 1 plus a over 2. Then, by what we said, there exists a lemma, there exists a capital N, such that for all n bigger than or equal to capital N, an, absolute value, and this should be nth root an, an, nth root of absolute value of an would be strictly less than b, which would mean that absolute value of an would be less than b to the n. This holds for n indices after that. Now b is less than 1, so sum of bn is converging. So what we do is we've split this series. We want to say something about the series, and this is a formal expression at first. We want to say something about the series an, and consists of two parts. The first capital N terms, and then the terms after that. Now this is a constant, it's a finite sum. And this is convergent, absolutely convergent. Why? Because for these indices, once n is bigger than that, absolute value of an is less than b to the n, and sum of b to the n is less than infinity. I mean, strictly speaking, only for these, when we're looking at these indices. Okay, so what are we using here? There's a general principle that we're using, is that if you have a series such that starting from some index you converge, then the whole thing converges. And the proof is essentially, this is a constant plus something converging. You have to do it a bit more carefully, but. Okay, so in our case, well, we already did this. We concluded by comparison test. So by comparison test, sum n equals n plus 1, infinity, an converges, since sum n equals n plus 1 to infinity of b to the n converges, as b is in 0, 1. Okay, questions about this? Okay, so it's actually, yeah, proving your root test is not very difficult if you have this simple property of lim sup. Okay, we will need to look at root test when we have nth roots. So there's another useful lemma that we have. This one I will not go maybe in full detail through the proof, but just give you the steps. So if you have a polynomial and you take the nth root of that polynomial, then this lim sup is equal to 1. In fact, the limit is equal to 1. Okay, so we want to show that the lim sup is bigger than or equal to 1. Well, there exists a capital N such that after that index, the polynomial is bigger than 1 because the polynomial is going off to infinity. So if we take the nth root on both sides, nth root is increasing, we get something bigger than or equal to 1. So all of these elements are bigger than or equal to 1. Therefore, their supremum is bigger than or equal to 1. And then we take the limit of those suprema, which is bigger than or equal to 1. This time the limit exists. So therefore, the lim sup is bigger than or equal to 1. One remark about this. The convenient thing here is I don't have to worry about any limit existing when I write this. The lim sups always exist. So this everything here is justified. If I went from here to saying that limit n goes to infinity of n square root pn is strictly bigger than 1, I would be making a small logical flaw because I don't know that this limit exists. I would be saying does not exist is bigger than or equal to 1. So writing limits is actually, you have to be a little bit more careful, but lim sups, you're not as careful, you need to be as careful. Now less than or equal to 1, it's again similar. You fix an epsilon, you want to show that the lim sup that you have is less than 1 plus epsilon. We fix a b plus epsilon. So what we will use is, well, the fact that this is a polynomial. It's a sum of terms that we can bound individually. So if we do an induction on the number of terms, we can prove that there exists a constant, since b is bigger than 1, such that the polynomial is growing slower than this geometric thing. But then the lim sup of nth root of Pn would be less than lim sup of n going to infinity of nth root of c b to the n. But, okay, b to the n gives me 1, and the nth root of a constant converges to 1. Okay, this is a fact that we would need, that we could prove. So we get that this is actually a limit, so this is equal to 1 times b, which is 1 plus epsilon. So what we get is lim sup is less than or equal to 1 plus epsilon. And we're done, because epsilon is arbitrary. Okay, so polynomials, nth root, what we do with those, we know. And why this is important here is that everything is perfect for this power series. If you take the nth root of here, what you're left with is absolute value of x and nth root of a absolute value of an. So if we want this to converge, we would hope that this would be less than 1. And that's what we will basically use. Okay, so let's state the theorem. But the theorem requires us to first define a notion of radius of convergence. Define a notion of radius of convergence. And what this is about is that, remember the pictures that from the Python simulations last time, or if you didn't see them, feel free to check. So you have this power series, a n x to the n. In our example, this was n squared plus n. And this series does not converge for all x. It only converged in some interval minus 1, 1. So the convergence happened here. And the radius of convergence is this size of this interval. Equals 1. And outside of this, nothing good happened. These things became nonsensical. The series became nonsensical. But okay, how do we find this radius of convergence? Well, motivated by the estimates that we saw and trying to sort of estimate this term, we want to do a root test here. So we look at the nth root of the nth root of absolute value of an. And there are 3 cases. If this is going very quickly to 0, then we define L as, well, if L is 0, then we define R as equal to infinity. If L is equal to infinity, we define R as equal to 0. And if L is between 0 and infinity, we define R as 1 over L. And this R is called the radius of convergence. So it is exactly should be this value that we have here. I mean, maybe just to slow this down a little bit. An example, if we have the power series A that we discussed last time, n squared plus n, x to the n. And, well, this is our an. So if we compute first L as the limit superior, n goes to infinity of nth root of absolute value of n squared plus n. Well, this is like the Pn lemma above. This is equal to 1. So L is equal to 1. So R, we're in the third case when L is between 0 and infinity, is 1 over L, which is 1. And this confirms our calculations on Monday that they were really correct. Okay, so what can we say about this? Okay, so if we we look at this series centered at some point x naught, the proofs we will do usually with x naught equal to 0. And if this is a power series, at this point, a formal power series, we don't know anything about it. And let R be the radius of convergence as defined with the limit superior, or the reciprocal of the limit superior. If R is positive, then the series converges pointwise on x0 minus R, x0 plus R. The series converges uniformly on parts of that interval, so not on the whole thing, but parts of it. On the whole thing, you are continuous, and on the whole thing, you are smooth. So just to give a quick picture of this, we have x naught. We have the radius x naught minus R, x naught plus R, and within this, you get convergence, continuity, and smoothness. And if you go to a strict part of this, if you exclude the endpoints, then you get uniform convergence. But you can play with this choice of where you put this. And this is kind of the thing that you have to worry about in the homework, because you get things like with signs, you cannot go all the way up to the boundary. So, but an example of this theorem application is if I define this power series, n sine n squared x to the n, then this defines a smooth function on minus 1, 1. And the reason for that is that if we compute the limit superior of n sine n, this is less than or equal to the limit superior of n squared of n. And by lemma, or you could prove it directly, this is equal to 1. So the radius convergence has to be at least 1, because it's the reciprocal of L, and L is at most 1. It could be bigger. Actually, in this case, it is equal, but it would require studying more carefully what happens to sine. So by theorem, it is defined and smooth on minus RR. Outside of R, you could say that this series is diverging. So if you take any point outside of this, then you don't converge. Any questions? Okay, so let's go. This is really takes only about 10 minutes, so we can certainly cover this now. So without loss of generality, let's make x0 equal to 0. And what we need to show first is convergence pointwise on minus RR. This is part of A and B, that this thing is defined. So, okay. And the reason for this is, what you should be thinking about is something that many of you noticed on the homework. So you're still doing the homework, but either you have noticed or you noticed that when you were estimating sine n, x to the n 2 to the minus n, and you wanted x to be in minus 2, 2, then the trivial bound that you would do would be 1 for the sine, 2 to the n, 2 to the minus n, 1. And this would be your mn. Well, this does not converge. So where is the trick? The trick is that if x is in the interior of minus 2, 2, then actually there exists an a between 0 and 2 such that x is inside minus AA. Actually, and for later purposes, we'll need to open interval minus AA. So how does that improve this estimate? Well, the coefficients we can't do anything about. Sine we can't do anything about. But this we can make better, a to the n. And then we get a over 2 to the n, and that gives us our geometrically convergent thing. So you can't work with the Folder interval directly. You have to work with a part of it. And this is one of the confusing things with power series. But the way to wrap your head around it is you focus, you can't work up to the endpoints. You have to cut away some small part around it. So, but let's first do the pointwise convergence. So we fix an x in minus RR. This is our setup. We choose an a so that x is inside, and I'll put it in the open interval because it's a little clearer for later purposes. And how would this be why is this the case? Well, x is in the interior. So one thing you could do, for example, is a r minus absolute value of x over 2. So notice that the interval depends on x. This is good to keep in mind, but so nothing here is uniform over all x. It's somehow conditional on some part of x. Okay, so but what can we do with the estimate then? Well, okay, so fn of x is absolute value of a and x to the n. And we want to estimate this from above. First, we just leave the absolute value of an, and then we put x to the n, we replace that by a to the n, and we call this mn. And we want to show that we have uniform convergence on minus AA, so we want to apply Weierstrass on minus AA. Closed interval minus AA. So, but to do that, we have to show that this bound that is valid on the full interval is summable. To do that, we have to apply the root test. So we take the nth root of mn. Well, what is this? Lim sup n goes to infinity of nth root of absolute value of an, and then times a to the n. Now let's do this in one line. This will converge to L, which was 1 over R. This part will converge will just be A. It's a constant that you can pull out of the lim sup. Now choice of A is in the interval 0 to R. So this ratio is less than 1. Therefore, by root test, sum n equals 1 to infinity of mn converges. Therefore, since this estimate was valid, this is valid for all points, all other points as well on minus AA, we are done with Weierstrass m-test. So, okay. Now, this is a sketch. So there's some order here that would need a few more words, but okay. So this gives us uniform convergence on minus AA. Since x eventually belongs into one of these minus AA, we get that f of x is defined. And we get that also, well, at this point, we don't get more. So now, okay, we want to prove, let's see what other parts. So now we have done convergence here. We have convergence uniformly on these parts of the space. We want to show continuity. This is kind of where we culminate this lecture. And this is the issue that you also want to address in your homework. So if you fix an x, you can find an a such that x is inside the open interval minus AA. By B, the convergence is uniform on minus AA by the argument above. So the series, if we define it as the infinite sum of a n x to the n, if we restrict this function to minus AA, this is continuous. And x lies in the interior of minus AA, which is the open interval minus AA. So the full function f is also continuous at x. Pictorially, you have x, you have this a that is a little bit around it. You know that your function is continuous on this interval. Because x is in the interior, the continuity is inherited at that x, even if you add the values that lie outside of this set. The only problematic points could be the endpoints here. You have to be careful. But okay, if we have this, then part D is all you have to add is you have to differentiate this series m times. And what you get is you get a polynomial thing times a to the n. And then what you do, you estimate that appropriately. So the rest of this, I will add a short video for Friday where I finish this proof about the differentiability. But it's basically the same bound with a slightly different twist. But thank you. If you have any questions or if you want to go back to the beginning of the lecture, feel free to stick around. Okay. See you, Bowen and Bingjing later.
See you.